Okay, so this is a different application I'm using to show you. It's one my mentor teacher showed me. I didn't have a lot of luck with the science applications on the K through 12, that K12.org site. So I went here to find something that I could use and that upper level science or social studies might be able to use for sustainability or the science of water and weather. Um, so for ISTE standards, what this one is going to cover is Standard 1, Creativity and Innovation. Students demonstrate creative thinking, construct knowledge, and develop innovative products and processes using technology. In particular, this is going to go down here on C, use models and simulations to explore complex systems and issues. And D, identify trends and forecast possibilities. So I'm going to take you over here to this application, which is from ASU's sustainability, School of Sustainability. And what it is it is a water model. It's a simulation of how to maintain water supplies and a bunch of different looks at the types of things that affect water and how water use affects the availability later on. So these pictures are really cool for younger kids who can't read graphs. Um, and then they've got things like the regional aquifers, which is a good thing. Some of the kids cover that in science. So I think that's in the upper grade levels, maybe fourth grade, but mostly fifth and sixth. And then sustainability is also covered in social studies, so that would be an option. But here it describes all of your policy choices and it gives you definitions of those choices and it tells you what zero stands for. So all of the water is going to agriculture here if it's on zero, or if 100, then all of the water is being used for the environment. Farming water here, zero is agriculture has access to all of its water and the cities are getting none. So you've got to adjust it so that the cities can get some water. So if you have it set on 80, then the city's only getting, then agriculture gets only 20% and the cities get 80. So it's kind of reverse on this one. And then water for the environment. Again, this is regular water, not reclaimed wastewater. And this is water that's left in the river, not being used or treated and returned to the environment. So a value of zero determines that no water is intentionally left for riparian habitat, whereas 100 leaves the maximum allowable amount of water in the river. And then we have change in per capita water use, which is 40 gallons a day per person. And then we have a change in projected growth rate, which values greater than 100 increase the population growth rate, values less than 100 decrease the population growth rate. So it tells you how to work all of these numbers and how to look at them. So a value of 130 will increase the projected population for your city of interest by 30%. So if you have it on 30, then you're going to increase population. Um, and then click out of that. You can scroll down. And what's cool about this is you can go and you can either do a regional look at things for all the cities' water supplies, or you can do bring it home even more for them by just having them look at Gilbert's water supplies. So right now everything is set on zero. So by taking water use for the environment, or that's being returned to the environment, so treated wastewater, and this is putting some of it to the environment, but by putting some of it to cities, so this is the amount of farming water you're actually using for cities here. And then leaving water for the environment, which we definitely need to do. 100% would be intentionally leaving 15%. 15% of the daily or annual river flow in the river. So that's the maximum allowable amount. So saying we do that and we don't change our per capita use, and we realize that 100% is actual. Okay, there's the change in growth rate at 150. So say our growth rate changes to, our growth rate slows down because of the economy or whatever. Well, let's do that. Then you go down here and you click on, darn it, where's my run model? My record button's in the way of my run model button. Let me zoom out a little bit here. There we go. Okay, run model. And see what that does to our picture up here. So by using wastewater, we're depleting our groundwater by 14%. You can see that red dip there. The river got bigger. The city, I'm not sure what goes on with this picture, but we have a very low personal use, and our population is looking okay. So let's take our water down because we're not leaving enough for the environment, and let's increase our city water because that's what we're doing, and lower our wastewater, and be honest about our per capita water use, because some of us take, showers that kill our water heaters, and they're 40 gallons just in the shower. So when we click on run the model, our river just shrunk, our groundwater stayed the same, our city population increased. We have another level of houses here. Our shower went up, and I didn't notice, oh, it's sustainable out to 86 years. Okay, so that's all showing you city stuff, but if you wanted to show something a little for younger kids, you could show them the regional aquifer. So this is where our aquifer balance is by 2050. Now, if we took our wastewater to zero, we increased our use in water there, we decrease what we're leaving for the environment. This is just to show the kids a change. What is it going to be like if we don't change things? So, and an honest, keeping our growth rate just at the same. Okay, let's run that model. And we are out of water in our aquifers, which is our regional aquifer. And then you can show them, and that's the Phoenix area, by the way. That's local. So it's a really interesting, and obviously this is taking a big dip here, but then you can turn around and you can show them, you know what, if we limit how much water we're using, conserve more water in the cities, okay, even a little bit more water, we start using more reclaimed wastewater, we put some water back into the environment, even not a big amount, okay, and we keep our water use reasonably the same, and we work on that growth rate issue. Let's see what it does to our aquifer balance. Look at that. We just made it all the way. Oops, let me get over to it. Or I'll click it here and bring it up. We just made it, we balanced everything out through 2050, and it's looking good just by those little changes. So it gives kids a good idea and a good understanding of what it takes. It gives us 98 years. So hopefully that'll be something you can use. I would use it in a lesson for sustainability. I would use it in a lesson on water management. I have one for the 7th and 8th graders that I'm doing involving a casino, that Glendale casino that they're wanting to put in. And I'm going to have the kids come in here and use these to figure out what's reasonable and what's not, and how much this one would go up in use, and how much water per capita would go up, and as well as the projected growth rate, because there's going to be an increase of people in that area. And then we'll run some models and see what happens as part of the lesson. So anyways, I hope you find this to be something that's useful. Again, here's the URL for that website. And I'm sorry I didn't give you more information based on the AZK12, but the links I tried to follow just took me back to AZK12, and then when I typed in the links, a lot of them were dead, or were pictures of planets and various Q&A type things. So they weren't technology, so to speak. So I really like this one because it's technology, it's usable, it's real life simulations, it's graphing, it's any number of types of graphs you want to look at. Um, you can look at water flows, you can, for older kids, supply, demand, water credits, groundwater credits, if you want to get into that aspect of it. So there's a lot of good stuff here, and it's all a lot of fun to play with. I've been having a blast doing this. So anyways, I hope you enjoyed the lesson and have a good day.